Hello, AP Chemistry students. This is Mrs. Altman. We are on video number 24, Chemical Kinetics, Part 6. Here are our objectives for today's video. Pause here. You don't need to draw the picture. So it is the collisions of the reaction that determine the rate of the reaction. So the collisions have to have enough energy to overcome the activation energy, and then the orientation of the collisions must also be correct. So those are the two factors. The picture that I have here is an explanation of why at higher temperatures you usually have higher reaction rates. And the reason why that is the case is because at higher temperatures you have a higher average kinetic energy. And so that means that each collision is more likely to have enough energy to overcome the activation energy. So if you take a look at it, the area under the curve, that area is larger for the black line because it's at a higher temperature, and the area underneath is smaller for the red line, which is at a lower temperature. Pause here. Right, so we're taking a look at what appears to be a first order reaction, or very likely to be a first order reaction. And we are seeing that the half-life in trial 4 is less than the other 3 trials. The reason why that is the case is because the temperature is higher in the 4th trial, and therefore each collision is more likely to have enough energy to overcome the activation energy, so the rate will be higher and the half-life will be lower. Pause here. So when we want to increase reaction rates, we might want to use a catalyst. A catalyst increases reaction rates. They don't appear in the overall chemical equation. They could either be something called a homogeneous catalyst. Usually homogeneous catalysts are going to stabilize transition states, and that will there'll be less of an energy hill, therefore there will be a greater rate going forward. And then there are heterogeneous catalysts. Those typically work with changing the orientation of the reactants. They're typically in a different state of matter, so metals are pretty commonly used for that. Pause here. You don't need to write the whole question out. All right, so we have an exothermic reaction, and based off of what we're seeing here, we're going to just assume that it's a one-step reaction. And we want to see how does the catalyzed reaction differ from the uncatalyzed reaction. So potential energy versus reaction progress. So for my normal reaction, I've got reactants, I've got an energy hill, and I've got products. So that is my normal reaction. For my catalyzed reaction, I'm going to have the same reactant, and it's going to have the same products, but the energy hill isn't as high, and so therefore the reaction rate will be greater. Here are the practice problems for today's video. Thank you so very much for watching, and have a great night.